Okay, so on to the next topic. We're asked to give the systematic IUPAC names for two possible organic products of such an oxidation of butene-1-ol. Now it says at the start here, consider the oxidation of alcohols. So if we're going to look at the oxidation of alcohols, when we start with an alcohol, when you oxidize it, you produce an aldehyde. And when you oxidize that again, if you keep going in excess, you get a carboxylic acid. So in this particular example, it gives us butene-1-ol. So butene-1-ol is this compound. And then it asks us what the corresponding aldehyde is going to be, because it's looking for two possible organic products of the oxidation of this. So the next one is the aldehyde. So your first product is going to be a 4-carbon aldehyde. So C double bond O and a H. And then you put in all of these. So again, it's looking for the names. So the name of this one is, well, butanal, but we can put in butanal, or we can put in butene-1-ol. Oops, sorry. We can put in butanal, or we can put in butene-1-ol, whichever one you want to put in. And then your carboxylic acid, again, is also going to have 4 carbons. So your 4 carbons in this particular example is going to give you butanoic acid. Then it says draw the structure of the organic product when butene-2-ol is oxidized in this way. All right, so let's have a look at butene-2-ol. So butene-2-ol, 4 carbons for the bute. 2-ol means it's on the second carbon. Now I'm working from left to right here. It really doesn't matter which side you work from. This is your butene-2-ol. Okay, and you are going to oxidize this. So when you oxidize this alcohol, again, you're keeping the same amount of carbons, except this time you're going to form a C double bond O. Now, why are you forming a C double bond O? Because this is a ketone. And you have to remember what you've got here. Butene-2-ol is a secondary alcohol. And the reason why it's a secondary alcohol is the carbon that's bonded to the OH group is bonded to 2 other carbons. So there's the first carbon, there's the second carbon. Whether there's a third carbon over here really makes no difference on the left-hand side, because that's not bonded to the carbon that's bonded to the OH group. So we've got a secondary alcohol. And again, when you oxidize a secondary alcohol, you end up with a ketone. So again, 4 carbons, and then surrounded by hydrogens. It asks you in this just to draw the structure, and it doesn't ask you for the name, but again, this particular ketone here would be butanone, or butane-2-ol would do as well. Okay, so let's have a look at part 3. Identify clearly which bonds in butene-2-ol are broken in this oxidation. Okay, that's fine. So what I would do here is I would redraw out the structure. So I would say there's your bute, and I would put in all the bonds all the way around. Now another thing I would do here is, this is normally just OH. Put a hydrogen in there for a second. So this OH, in this circumstance, I would actually put in the bond here. So you have an oxygen bonded to a hydrogen. When it asks which bonds are broken, it's sufficient to draw the bond here, because that bond is broken, which allows for the double oxygen to suddenly come into play. And also this bond here, this is also broken. You can write this out, of course, if you want. You can say the single bond in OH is broken, and you also have to say the single bond in CH is broken. However, if you do go this route without drawing a structure, you need to say which CH bond it is, because there's lots of CH bonds. So the single bond in the CH, and then you have to say that is attached to the carbon that is attached to the OH group, which there's a lot in that, okay? So it might be easier just drawing the structure. Okay, moving on. The ester formed from methanol and propanoic acid is found in many fruits, and you've got to draw the structure of this ester. So if I was approaching this, I would have a look at methanol. I would do this on my page, plus propanoic acid. And you should know that an alcohol and carboxylic acid is going to give you an ester and water. That will help me figure it out. I start with methanol, which is an OH on the end of a methyl group, and then you've got your propanoic acid. So propanoic acid at this time is 3 carbons, double bond O, O single bond H, and that's your propanoic acid, and you're going to form an ester. So when you've looked at so many ester reactions, you should be able to spot that that OH there and that H there are going to leave to form water. So that gives you your H2O at the end. So what happens then in the meantime is this particular group here, which is your methanol, that goes in place of the hydrogen here. It's a substitution reaction. Hydrogen leaves, methyl group goes on, and then you just have to draw it out. So you redraw out the propanoic acid, except this time you put the methyl group in. So it's C, bond C, bond C, double bond O, and then O, and then you put in your CH3, which I'll just put in blue so you can see where it's coming from. Go back, just make sure all your carbons have got the 4, and then of course this one wants you to draw the structure of the ester, so that is it. There's your structure right there. It might ask you to name it. It doesn't in this question, but if it wants you to name it, you should. Throw it in anyway just in case. We have 1, 2, 3 carbons in a row, so this is going to be prop. It's an ester, so it's an O8. And then what type of ester is it? It's this type of ester. It's a methyl propanoate. If you knew this, if you were learning this and you knew it off by heart, by all means, just put down the structure. There's no problem. And again, this structure can be written in other ways. So for example, you can write it as CH3, CH2, COO bracket CH3. That's perfectly allowable as well. It's up to yourself. Okay, moving on to 2015. Answer any of the 2 parts. So part A was organic chemistry, distinguish between saturated and unsaturated hydrocarbons. Now that's from a different section, but we know what that is. So saturated, of course, contain single bonds, and unsaturated contain double bonds or triple bonds. And there's tests for that. The test being acidified potassium permanganate or bromine water. Describe how you test a given hydrocarbon for unsaturation. So again, that's the test. That's from another section. You hopefully know that. In 1865, Kekule proposed the structure for benzene. How many pi electrons are there in benzene? And then explain whether or not the Kekule structure correctly describes the number and the distribution. Okay, so there's a little bit in this. Now we've gone through this in a previous question, so I won't go through all the theory again, but let's have a look at these pi electrons. That's phrased slightly different than what we originally looked at. So first of all, let's have a look at benzene. So if I redraw out the benzene structure, we can go and have a look at the pi electrons and see where they are. So misreading this question is very easy to do. It says how many pi electrons are there in benzene, and this is the key word here, electrons. It doesn't ask how many pi bonds, how many pi electrons. What's the difference? Well, we know from looking at a double bond that one of the bonds is a sigma bond and the other one is, of course, a pi bond. And that is this one here is a pi bond. But a single bond, whether it's a pi bond or a sigma bond, involves 2 electrons being shared. So you actually have an electron here and an electron here. So this here is a pi electron, and so is this one. So that means for a pi bond, for 1 pi bond, you have 2 pi electrons. So that means if you have a pi bond here in this double, you have a pi bond here in this double, and you have a pi bond here in this double, each double holds 2 pi electrons. So you can say, therefore, you actually have 6 pi electrons in benzene. However, it doesn't ask this question. However, you have 3 pi bonds, and you got to know the difference between them. Then it says, explain whether or not Kikuli's structure correctly describes the number of the pi electrons and the distribution of the pi electrons. Okay, so looking at number part 1. So does it correctly describe the number? So does this particular shape describe the number? And I would answer yes, it does. And the reason why it does, and this is your explanation, is it clearly shows 3 double bonds. And because it shows 3 double bonds, that implies you have 3 pi bonds or 6 pi electrons. So that's the first one. However, then it says explain whether or not does that structure, does that shape, does that explain the distribution of pi electrons in benzene? Now we know from previous examples how the electrons move around benzene. The electrons move around benzene in a delocalized fashion, and that's not seen in this structure. So in this particular example, I would say no, it doesn't accurately. And the reason I would give is it doesn't show that electrons are delocalized. If you wanted that, you know, this benzene structure here would be far more appropriate, and that shows that there's delocalization amongst the electrons. Finally then in the last bit it says give one piece of experimental evidence in support of your explanation to part 2. So you've got to explain this using experimental, and one of the things you could put in here is just that benzene is a very stable compound. It's not necessarily looking for a test. Benzene is a stable compound and it's relatively unreactive. So that's all you need for that. 2013. Describe the structure of benzene in terms of a few bits. So we'll have a look at this in the next video.